Let's talk some forces. So first off, we're going to start in reverse from the way we did this in class. We're going to start with the third law. First thing to remember is that a force only occurs when two different objects interact, okay? So like a car can't produce a force on itself. It has to have some other object from the outside act on it to produce a force on it. These forces always come in pairs. They always act between the two objects. So like, for instance, here's an apple. I'm holding the apple up. I'm pushing the apple up. The apple is pushing my hand down. My hand will get tired from holding it for a very long time, and it doesn't fall because I'm pushing it up. The forces between the two objects, this force pair, is always equal and opposite, equal in magnitude, opposite direction, and they always act on the two different objects. Here's an example. A hammer is striking a nail. The hammer pushes the nail down with a force, and the nail pushes the hammer up with a force. This force pair is exactly the same. The hammer drives the nail in, and the nail stops the hammer from continuing to move. A skydiver jumps out of a plane. The earth pulls the skydiver down. The skydiver pulls the earth up. But since the skydiver has a small mass, they will have a large acceleration, and the earth, which has a large mass, will have a smaller acceleration. So here we have a person leaning up against the wall. So their forehead pushes against the wall to the side. The wall pushes them back, keeps them from falling over. Their feet push down on the floor pushes back up on their feet. So if we look only at the forces on the person, those forces would be this one pushing on the person and this one pushing on their feet. Those are the only two that affect the person. So these two interacting pairs never cancel out. That's a common misconception because they act on different objects. One affects the wall, one affects the person, one affects the floor, one affects the person. Okay, now let's go on to Newton's first law, the law of inertia as it's commonly referred to. An object can't supply a force to itself. So by itself, it can't make itself do anything. Like for instance, a propeller on a plane. It's like, well, isn't the propeller pulling the plane forward? The answer is yes, but the propeller is pushing the air. So if there's no air there, if we take that plane out in space and the propeller spins, it has nothing to push on, so the plane can't go forward, because the air can't push the propeller and the plane forward. Okay? So if the object is already at rest, it'll just stay there without an outside force. If an object is moving, it will move in a particular way, a constant straight line velocity motion. Okay? So objects have like this it's really one type of natural motion. When there's no forces acting on an object, it has a constant velocity, which could be zero. So it's either going to move at a constant speed rate in the same direction all the time, or it's going to sit still, which is a special case where the velocity is zero. So the natural rest and natural constant velocity, this behavior of objects is called inertia. Objects don't want to change their motion because they naturally want to sit still or naturally move in one direction. Okay, there has to be a force to make them stop doing this or to make them change their motion. So the bottom line is, if the forces on an object all cancel out, then the acceleration will be zero all the time, every time. Or conversely, if the acceleration on the object is zero, then the forces on it have to all be canceling out, or there's no forces at all. Okay, let's talk about the second law. What happens when there is a net force? Okay, so this is the way they write it on the AP exam, so I wrote it the same way here. If there is a net force, then the object will accelerate in the same direction as the net force. But the bigger the mass is, the smaller the acceleration will be. So these two things fight each other. Bigger the force, bigger the acceleration, bigger the mass, smaller the acceleration. Notice that the first law, the law of inertia, is a special case of the second law, where the force is zero, so the acceleration is zero. Okay, the bottom line for the second law is this. If there's a net force, the object will accelerate in the direction of that net force. The equation F equal ma only relates forces to the mass and acceleration. If you want to know other things like what the velocity of the object is or what its displacement is, you're going to have to use kinematics because we don't know from F equals ma. All right, so let's go down our laundry list of forces that we're likely to see in mechanics. First is gravity. Here it is, F sub big G, G m1 m2 over r squared. Remember that big G is just a constant. This is the one that we use when we have astronomical objects, things far away from the Earth, or when we get off the Earth's surface. And remember, the force between the two is equal and opposite all the time, even if one is bigger than the other. It doesn't really matter. Specialized equation for gravity is called weight, and we only use this one when we're near the surface of the planet, like near the surface of the Earth. The weight will be mg, where g for the Earth is 9.8 meters per second squared. If you're far away from the surface of the Earth, then we can't use this specialized one, okay? So this force always pulls you straight down. And there's an equivalent one pulling the Earth up, but I just wrote the one that for the person laying down here on the floor. Now remember, this equation here and this equation here are exactly the same at the surface of the planet. So if we set them equal, the mass of the object cancels out, and we'll find out what G is, the gravitational constant, or the gravitational field, or the acceleration caused by gravity, they're all the same thing, will equal this. Now we're going to talk about three contact forces. The first one is normal force. So this only occurs when the objects are in physical contact. So when you put a bowling ball on like a bed or like the floor, it compresses the system. And so the system pushes back. So here is a little sketch of what atoms would look like inside of an object. And you put a bowling ball on it, it's going to smash the atoms down. They're going to try and snap back into their original shape. So you get what's called the normal force. So they're equal and opposite forces again. So the normal force from the bowling ball is down, and the normal force from the ground is up on the bowling ball. They have to be in contact for this to occur. So if you jump off the floor, normal force between yourself and the floor disappears. Friction. Friction occurs when you try to slide or actually sliding against something, okay? So you can see it in your hands. If you try to move your hands past each other, you'll see your skin flex, okay? And that's what we see here, a foot flexing what's called shear against the atomic structure. So when you try to slide backwards, the force on you is forward, and the force, a force on your foot is forward if you try to slide backwards. Now the equation for this is the force of friction is less than or equal to mu times the force normal. We're going to talk about this less than or equal to in just a little bit, but the normal force is how hard the two subjects are pushed together. So the harder you push them together, the bigger friction force can be. And the mu has nothing to do with anything else but what the surfaces are like. So the rougher the surfaces or stickier the surfaces are, mu gets bigger. And the slipperier the surfaces are, mu gets smaller. And if mu is 0, then they're frictionless. So when we have a frictionless surface of science, mu is 0. Okay, tension. Tension is when you grab an object and pull on it. So like if I take this and I pull on this marker, I'm stretching the atomic structure out, so when I pull out, it pulls back in all the way through the substance. So if you're playing tug of war with a rope, then the tension is equal all the way through that rope. So it's equal on both ends, pulling inward as it gets pulled outward. Spring force is very similar to tension and normal force. So when you pull on an object, it tries to snap back. When you push on the object, it tries to snap back outward from its compression. Except in this case, the object actually stretches and compresses enough that we can measure it. That's what this number over here, delta x, is. So here's the original length of the spring, and then you compress it, and you can measure how far it compresses, or it stretches and how far it stretches. That's what delta x is, then the length change from its original size. If you compress it, it will push outward through the entire system. If you stretch it, it'll pull inward through the entire system. Now, how much does it pull or push back? Well, that depends on K, its spring constant, also known as a force constant. So the bigger that number, the more force it has for every meter that you stretch or compress the object. All right, so now let's talk about the procedure for setting up and solving F equals ma type problems. We talked about this in class a lot. So remember, very first step is to draw your free body diagram, also called a force diagram. Try your best to draw your arrows always pointing away with an arrowhead on them. On the AP test, if there's a grid, make sure the arrowhead goes to a grid line. Always try to make them the correct length and point in the correct direction. If they're at an angle, draw them at an angle. If they're going to be equal, mark them as being equal. Step number 2, determine if the object is accelerating. This is critically important because it tells us whether we have an F equals 0 problem or an F equals ma problem. Next, set up your coordinate system so that it's always parallel and perpendicular to the acceleration. So if you're accelerating up, XY works great. If you're accelerating down an incline, then you want to set it up so that it's always parallel and perpendicular to the incline or to the acceleration. Next, for your 2 directions, build your F equals ma and then solve if you have numbers, and if not, you'll just end up with symbols. So here's an example. So we got a child that's pulling a box across a rough surface at a constant velocity. So constant velocity means the acceleration is 0. So look for those words. That's important. That means in this direction the force is canceled. Since they didn't tell us about the vertical direction, we'll also assume that it's not accelerating up and down. So we have a tension from her pulling. We have a normal force from the floor. We have gravity down and a friction to the left because it's sliding to the right. Now look for those words: rest, constant velocity, not accelerating. That means acceleration is 0. That means the forces all cancel out. And we like those types of problems because they're easier. If the object is accelerating, that means speeding up, slowing down, or changing direction. Remember that. Changing direction means circular motion, and it's accelerating. Then we have an F equals ma type of problem, and that will be just a little bit harder because the forces add up to equal m times a. Remember that an object can be at rest in one direction or moving at a constant velocity in one direction and accelerating in a different direction. An example would be like a car at a stoplight. They hit the gas. They're accelerating, say, in the x direction, but they are not accelerating at all in the y direction. In fact, they're at rest in the y direction unless they're climbing a hill. Just a couple of things about acceleration. Remember that if there's no gravity, or I'm sorry, if there's only gravity, then you're in free fall and you'll accelerate down at 9.8 meters per second squared. If you're on a different planet, that number will be different. If you're on an incline, you'll accelerate down the incline or along the surface of the incline. If you're changing direction, your acceleration will always be towards the center of the arc or circle. Okay, so for our girl pulling along this box, she was not accelerating the box, so there's no acceleration at all. And since we have 3 forces that are in the vertical and horizontal direction, an XY coordinate system seems the easiest. That means we only have 1 force that's not in those directions, so we'll have to take care of that. So now we build our F equals ma for our 2 directions. So up, down, fine. Left, fine. At an angle, that's a problem. So tension we have to split into its horizontal and vertical components. And once we do that, we can set up our x and y direction. In the x direction, we know the forces cancel out to 0. We know we have a force to the right, and we have a force to the left. So one positive, one negative, and so they'll be equal. So the friction force equals the cosine component of the tension. In the up and down direction, we know our forces cancel. So we have 2 ups, 2 positives, and 1 down, 1 negative, or the ups equal the downs, and our tension force has a sine component. There you go. That's it. So let's practice a couple of more. So here we have a cow on a skateboard, a frictionless skateboard of science, and accelerating down an incline. Here's our free body diagram of the cow. We have a normal force that's perpendicular to the surface. Normal forces are always perpendicular to the surface. So if our surface is tilted, then our normal force is tilted. And gravity is always straight down towards the center of the earth. So these two will not cancel out because they're at angles to each other. So we have an acceleration down the incline. So we're going to set up our coordinate system, now that we know that we're accelerating, with one axis parallel and one axis perpendicular to the acceleration. So in the parallel direction, our forces will be F equals ma. But in our perpendicular direction, our forces must cancel out. So we build our F equals ma and solve. So in the perpendicular direction, we have a normal force and we have the perpendicular component of gravity. They must cancel out. And so mg cosine theta equals the normal force. And in the parallel direction, parallel to the acceleration, we only have the parallel part of gravity, which is mg sine theta equals ma, the acceleration down the incline. And so the m's cancel, so the acceleration down the incline will be g sine theta. Let's do one more. Here's a rocket. It's got its engines firing, it's launching off the launch pad, it's accelerating upward. So our free body diagram is only y components. So we're accelerating up, so our coordinate system's a piece of cake, x, y, and we know that we're accelerating up in the y direction. So this one's a pretty simple one. In the y direction, we have a positive force up and a negative force down, and they must equal ma in the y. Okay, a couple of things to be aware of. We have lazy forces. Normal force, static friction, tension, only do what they absolutely have to do and nothing more or less. They're not like weight or gravity where we have an equation and we can plug them into the equation. They're always equal to this value. The lazy forces, they never have a set value, okay? They depend on the situation. So for instance, the more you push on a surface, the more it pushes back. If you try to slide your foot across the floor, the more you push backwards, the more the floor is going to try to keep your foot from sliding until it actually slides. And the more you pull on a rope, the more it's going to pull back. Now, this all occurs because these solids are made of an atomic structure that's trying to snap back in position. So it depends on how much force you apply to them, and then they'll apply a force backwards depending on what you're doing to them. So here's normal force. It's some common misconception that the normal force always equals mg. That is not true. For a child with the wagon that we did earlier, the normal force is equal to mg minus ft sine theta. For the cow on the incline, the normal force is equal to mg cosine theta. If you're in an elevator accelerating upward, the normal force has to be greater than your weight. Or if you're accelerating downward, the normal force is less than your weight. So be careful about the normal force. It's not mg all the time. Second one to be careful of is tension. Tension depends on how much the string is being pulled on. So here's an example. Say you have a yo-yo that you're just holding there by the end of a string. Well then, if it's not moving, then the tension force up will equal mg. These will be the same. But if the yo-yo is accelerating up, then the tension force has to be greater than mg down. Or if the yo-yo is accelerating down, then the tension force must be less than mg. And here's friction. So here's an example problem. A 20 kilogram box is pulled to the right by a force of 10 newtons, but remains stationary. The coefficient of friction between the box and the floor is mu equals 0.5. Calculate the frictional force acting on the box. Now, key thing, remain stationary. That means it's at rest. All the forces must cancel. Now, here's the common mistake that a lot of students make is they say, hey, force of friction, mu normal. And then, well, in this case, the normal force does equal mg, so they just plug that in. They plug in their numbers, they get 98, they write that number down, and they're done. Except it doesn't make any sense. So how can the friction force backwards be 98 when the force forward is only 10? That means the box would accelerate backwards in the opposite direction you're pushing it. That makes no sense whatsoever. So remember, this less than or equal to for friction means it can be as high as 98, but it only needs to be 10 to remain static. So that's all it'll do. Since the box is not accelerating, the friction force is equal to 10 newtons, and that's it. It won't move. All right, that's it for now. Our next video is going to be about some special cases for forces, and then we'll work some practice problems. See ya.